Now for the final 2D NMR spectral labeling. This is the COSY. I like the name COSY. So COSY is just correlation spectroscopy. In this one, we correlate the proton NMR to itself. So this one's the head core we just did correlated carbon to proton, heteronuclear. This one correlates proton to proton. That might not make any sense at first, but I'll explain it. It'll make sense. So initially, we have to notice that this is the regular proton NMR, and it's got its scale down below. Here's the other 1D proton NMR scale over here. I blew it again. I cut off the acidic OH. I think it's because it default cuts it off because it doesn't have a correlation, but I like to see the lack of a correlation. My mistake. Rusty. That's okay. So let's label the the hydrogen signals as we normally would. So this would actually be signal B right here because A was cut off. A's over at like 12 parts per million. A cut off. And so that's B, C, D. So I've got that labeled. And then we have the exact same spectra on the vertical axis here. This is B, C, D as well, and A is cut off. A would be out here at about 12 because you see this is 8 parts per million. This is this is 9, and then 12 would be out there. Okay, and then let's label our molecule too to make sure we got the right idea. So this is, remember, A, the one hydrogen singlet, and then B and C are these guys. So if I'll go X again, X, 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 X equals B or C. And our integration, if you remember, was 1 hydrogen for B's signal, and C was 3 hydrogens overlapping. So 3 of these X's is C. Then D is the methyl, because it shows up at around 2 parts per million. Okay, so on the COSY, there's a diagonal set of signals that don't tell you anything. I'll show it to you. So if you draw a line diagonally through here, those signals don't help you. All they do is tell you that D corresponds to D, and that makes sense because D is D. And then, for example, C corresponds to C. Doesn't help you. And B corresponds to B. Doesn't help me at all. So those don't help you. It's things off that axis that help you. This one's going to help us. That tells us something, and that tells us something. This is just some noise. I'm not sure what that is. Something in there because you don't see a signal here, so I don't know what's going on. Anyways, so the one thing we do see though, when you only have a peak on the diagonal axis, that means you don't have any coupling, because there's no the signals off of the diagonal are telling you, oh, you're a hydrogen that's coupling to some other hydrogens. So this D doesn't have any signals on either side of the diagonal, so it's not coupling anything, which makes sense because we know D is a 3 hydrogen singlet, right? It's this methyl. It's not coupling, it's a singlet. All right, so now let's look at the other ones though. And let's start filling in the table. I'm gonna fill in my correlation table. So I have, zoom in on my end. Okay, so hydrogen group A, coupling partner 1 or 2. I cut it off. A was this one. It would have none, but I cut on accident. Ugh. I didn't actually cut it. It auto-processed into us, cut out, and I didn't realize it. I should have. That's something that it was the end of the day. I was hungry. So I can't, does it agree with structure? Can't tell. Okay, so B B here, as I come down, it does have a correlation, a correlation off of the axes. It correlates to C. See that? B comes across to C. So B couples to C, and that's the only correlation it has. It doesn't have like a correlation to D, or so it's done. B goes to C. And does that agree with our spectra? Yes. Well, it does, because B is one of these X's. So let's say this is B. Then this could be, or that could be C, because they couple, right? They're within the bond lengths. So does it agree with the spectra? Yeah, sure does. Okay, now next up, C. Does C couple correspond with anything? When I come down, C, it initially hits the diagonal peak, which tells me nothing. It's just the C to C. But then there is an off axis, off the diagonal, and there it is, C to B. C couples to B. And does that make sense? Yes, because we already know B to C, C to B. It should make sense. So yes. And you'll notice with these COSYs that they're symmetric about the diagonal, because B will couple to C and C will couple to B. So that's it. And C is what of these X's, of these four X's, one of them is B. Let's say this one is B. Then B would be coupling to this C and that C. And then if these three are C, that one doesn't couple B, but these two do. And since they overlap, you see that there's some part of it that couples. And that's, then in D, let's do D's last. So D, does it correlate with anything, couple with anything? It couples with itself, but that doesn't help us, but it correlates with itself, but nothing on the axis, nothing here. So D, coupling partner 1, none. Oh my goodness, why does it have to do that? None. Okay, so does that correlate, or does that agree with our structure? Yes, because we said D is a 3-hydrogen singlet, it has no coupling. So yes. So great, but I cut out the acidic hydrogen. Sad face. Does that look sad? It's confusingly sad. Put a nose in there and make it really sad. Okay. So yeah, that's it. So COSY, it's interesting. It tells you which hydrogens couple to each other. For this simple, well, this molecule is pretty complex, but for other molecules, you can get more out of this than we just saw. For us, I don't love COSY as much, because a lot of times you'll see correlations that don't make sense, don't agree with you. So you're like, oh, wait, what does that mean? Might be just that our NMR is only 60 megahertz. I'm not sure. Okay, so now I'll have you do this same labeling on the Google Doc.